Okay, we'll start today's class. So yesterday we finished till ionic product of water and how pH and pOH are related. Moving on to next, very important, Sorensen's pH scale. As I told, a pH scale which is actually developed, which is an arbitrary scale, which has been considered. The name of the scale is Sorensen's pH scale. So it looks like this, as you can observe. So one side you find the pHs, the other side the concentration of H plus ions involved. So what would they be considered? So in general, as we know, pH ranging from 0 to 7 are more acidic, and 7 is neutral, which is of pure water, and above 17 it's all basic, which is sodium hydroxide. Clear? So this is Sorensen's pH scale. Clear? So moving on to next very important topic for 5 or 10 marks. Please note. So very important question for 5 or 10 marks. So they'll ask is, so say now I give you an unknown solution. Okay. So I just give you an unknown solution and ask you what is the pH of this particular solution. So how would you determine pH of a particular solution, whatever given by me? So what would you do? It's an unknown solution I'm giving you. I'm asking you what is the pH of it. Find out and come. So what would you do? I hope my question is clear. Try to answer. That's okay even if you're wrong. Whatever you feel, answer. Are you getting my question? Are you able to hear me? Yes, someone answer.
Yes, ma'am.
Yes, just guess. So if at all, if I give you an unknown solution, so how would you determine pH of that particular solution? Simply just give a try. That's okay and if you're wrong.
Ma'am, it's a log of
Litmus test.
No,
ion concentration.
my question is, I give you an unknown solution. Okay. So, and I just ask you, just tell me what would be the pH of this particular solution. So how would you come to conclusion? What is the pH of that particular solution? What would you do? I'm not asking what is pH definition. I'm asking you, I just give you an unknown solution and ask you try to find out the pH of the solution. So how would you determine pH of the solution?
And use a pH paper
Right? Okay.
or indicators.
Okay. You use pH paper. So how do you do that? And what is the conclusion? An indicator, what is the conclusion? Please elaborate on this. What you know, it's fine, even if you're wrong. Yes, go ahead.
Ma'am,
Yes.
if it turns from blue to red, then it's acidic,
Okay.
and red to blue is basic.
Okay. So this pH paper test. Okay. How about indicator? Your name, please. Niharika? I don't know. Is it Niharika or Tanya? Who is it? The person.
Tanya.
Okay. Yeah. Yeah, go ahead. How about indicators? You are right. That's okay. Answer.
Ma'am, is the same with indicators also. Blue indicator turns red.
Which is that a slight change. Indicator is the right answer, but the answer given is slightly changed. Okay, let me explain you. So in general, the pH, different pH, how to measure? As you said, commonly we have pH paper as such, which just tells you whether the solution is acidic or basic. But precisely if you have to tell what is the exact pH, so say now you call it as acidic. So how much acidic is it? Is it pH 5? Is it pH 1 or 1.5 or 4? How much is it? So how do you conclude with that? So just for that, there are two different methods. One is known as colorimetric method. The other method is known as electrometric method. Again, I'm telling, very important for 5 or 10 marks, different methods of determination of pH. Okay. So first method is known as colorimetric method. Second method is known as electrometric method. So in case of colorimetric method, it is basically based on appearance of the color. Okay, we conclude the pH of the solution based on color. Okay, just for now time being, remember this. We'll go ahead in detail. And in case of electrometric method, with the use of an electrode, we are going to check the pH. So out of colorimetric method and electrometric method gives us the exact reading than colorimetric method. So even colorimetric method, we do get it, but plus or minus 2 or plus or minus 0.5 would be the difference. But electrometric method directly gives us the exact value of the pH, whatever we are supposed to determine. Clear? So moving on to first colorimetric method. So as I said, it is based on the color. As you people said, it is right. One is the pH paper method. So the color change in the pH paper, you tell whether the solution is acidic or basic. So that is one of the steps involved in the colorimetric method. So more than that, before we go on to it, for colorimetric method, as you said, it is based on the indicator. So anyone till now you would have used indicator. What do you mean by indicator? What is indicator? Anyone? What do you mean by indicator? What is it? And examples if you know. What's an indicator?
Ma'am, it's a solution or chemical substance that is used to
Name
determine the
please.
endpoint.
Tell your name, no please.
Shubhayan, ma'am.
Okay, yeah, go ahead. Yes, answer.
It's a solution or chemical substance
Okay,
that is used to determine the endpoint of reaction.
very good. So how does it tell you the endpoint? How does it tell you the endpoint?
By color change.
Color change, very good. How does it change the color? You're right, you're perfectly right. Whatever you both answered, it's right. So in detail, if we have to go, how does it change the color? What is the
Ma'am, it
exact?
reaches its equilibrium, ma'am.
Okay, equilibrium from where? From when? How? Okay, try at least. When does it reach equilibrium? Okay, shall I answer? So in general, the indicators, whatever we are calling, these are mixture of weak acid or salts of the same weak acid or weak base mixture as such. Okay, so as we know how electrolytes are, when you add it into water, they dissociate into ions, right? Similarly, any indicator also behaves like the same. When you introduce them into water or any medium, they split up into ions. Okay, they split up into ions. Based on the change in the pH, they show the change in the color. Clear? Based on the change in pH that would takes place, they show the change in the color. That is, for example, whenever you add indicator, initially you would have added. On adding, say now it's an experiment having HCl and NaOH. Okay, you add an indicator. Example, what indicator do you add to HCl? You have taken in the not in the beaker, in a conical flask HCl. Okay, say 0.1 normal HCl. And you add what indicator to HCl when you are taking NaOH as a titrant? Anyone? You have taken HCl in the conical flask, and in the burette you have taken NaOH, 0.1 normal each. Okay, so what indicator do you add into HCl? 0.1 normal HCl. Name of the indicator? Sorry? Yes.
Phenolphthalein, ma'am.
Right, phenolphthalein. So just assume, okay, we'll move ahead. So indicators generally It's an alternative method. As I said, the perfect method is the electrometric method, but still you get an appropriate, not exactly, but on an average you get the value of the pH, okay, for determining the pH of a solution. Indicators are either weak acids or bases that exhibit, it's actually a mixture of both, okay. It's a mixture of weak acid and weak base, which the indicators chemically. So they exhibit the color change based on their degree of dissociation, okay, that is they dissociate. So based on to what extent they dissociate, it depends on what is the pH at that particular moment, okay. So based on the pH change, they show the change in color. For example, before you start the experiment, you would add phenolphthalein, right, to the HCl. What would be the color? What would be the color? The contents in the conical flask after adding phenolphthalein. I'm not talking about the end.
Pink, ma'am.
Initially,
No color, ma'am.
no color, right?
Colorless.
So here what happens, indicator now is in which solution? HCl solution. What is the pH of HCl? What is the pH of HCl? It's acidic, right? So here what happens when you add phenolphthalein in acidic pH, it is colorless. So what you do further, you keep on adding NaOH, right? You do the titration wherein you keep on adding NaOH. So on adding NaOH, what happens? You are indirectly introducing what into the conical flask? NaOH, OH minus ions. Indirectly you are introducing into the conical flask. Thereby what happens to the concentration of H plus? That keeps on reducing. Or indirectly what happens to the indicator is that in at a particular pH it starts ionizing. Okay, I'll show you here. So showing a color change. So consider the indicator. So what happens when you add it into water is that this is an indicator. When you add it into water, it will dissociate into H3O plus and ion minus ion. Okay, so this is an acid color, this is a base, so it respectively gives an acid and base. So what do you call such reaction wherein you are getting an acid and base reacts to give one more set of acid and base? Yesterday I told you, when a reaction between an acid and base is giving rise to one more set of acid and base, you call such as?
Conjugate base, ma'am.
Right, conjugate acid base pair. Very good, it's right. So just assume for this particular reaction, you are applying law of mass action, okay, which is nothing but product of the concentration of the product to that of the reactant, whatever is present, concentration of the reactant. So Kin, whatever I have considering, is nothing but a constant, okay, and concentration of the product, okay, H3O plus and ion minus divided by H ion. Clear? So amongst this, we are just calling it as equation 2. So amongst this, one second, amongst this, H ion is nothing but the unionized form of indicator. Ion minus is nothing but ionized form of indicator. This is nothing but before it has got ionization or dissociation. This is nothing but ionized form of indicator. And this is nothing but water, that is H3O plus, which is nothing but the hydrogen ion. So in general, H ion is nothing but the unionized form of indicator. Ion minus is nothing but ionized form of indicator. Kin, whatever we are considering, is nothing but a indicator constant. In general, it's a constant. Since here we are considering an indicator, so it's calling as indicator constant. Till here, anybody has any doubt? Anybody has any doubt? Is it clear? Am I audible? Is it clear?
Yes, ma'am.
Okay. So just imagine
Yes, ma'am.
we are adding acid. Okay. On adding acid, what happens? We are directly introducing H plus ion. Yes or no? Because we are adding acid, acid has H plus ion with it. So indirectly we are introducing H plus ion, or the concentration of H plus ion increases, right? Thus giving an acid color. Because we are directly introducing an acid which indirectly increases the H plus ion, whatever color we get is nothing but acid color. Okay, so if a base is added, the amount of H plus ion decreases and H OH minus concentration increases. Yes or no? If a base is added, it has OH ion with it. So you are introducing OH ions. Indirectly, what happens? Concentration of H plus ion decreases. Thereby, basicity increases or alkaline color predominates. Okay, so due to the increase in the ionized indicator. So indirectly, the color of the indicator is a function of pH. Okay, at one particular pH, it will be acidic color or it could be colorless, or on ionization, it gives a basic color. Clear? As in the case of as we gave an example of HCl and NaOH, because you started adding base, there was dissociation of phenolphthalein leading to the color change from colorless to pink. So pink is nothing but basic pH. So acidic pH, what was the color? It was colorless because phenolphthalein was in unionized state. Is it clear? Phenolphthalein, as soon as you added into the solution, it was in unionized form. Okay, because you started adding NaOH to the solution. This is the example what I gave earlier. Conical flask with HCl, and then we are adding phenolphthalein. Titrant we are using is NaOH. So because we are adding NaOH, what happens? H plus concentration which is present in the HCl decreases and OH concentration increases. Okay, so because of which basicity is increasing. This is about the pH. What happens to the indicator which is also added along with the HCl? The phenolphthalein starts dissociating because of the addition of NaOH, whatever we have done. So finally what happens is that because of the dissociation, as you people said, the equilibrium, whenever it is being reached, you get the color change. Okay, because of complete ionization, you get the color change to pink. So that indicates the end point. That means how much ever H plus ions were present in HCl has got neutralized by the OH minus ion which you are introducing through NaOH, which is being shown by the indicator similar to that of, because even that is undergoing ionization. When the ionization of the indicator stops, it gives the end point. Clear? Do you want me to repeat or have you understood? Please let me know.
Understood, ma'am.
Understood. Okay. Just what we are doing further is we are rearranging this particular equation. Fine. We are just considering H3O plus. Just consider H3O plus here itself. KIN. So here it's this particular term is dividing. So when we take it to this, what happens? It will multiply KIN into HIN. And this, since we are keeping H3O plus as it is, so this term, it is multiplying here. If we take it this side, what happens? It will divide. So we get is H3O plus is equal to KIN, HIN divided by IN minus. Is it clear? We are just we are rearranging this particular equation wherein H3O plus we have to consider. So just keeping this as it is in this side only, or if you want to take, you can take it this side. Okay. So instead we are keeping this as it is and KIN as it is. So this, because it is dividing, if we take the other side, it will multiply. So KIN into HIN. So since here it's multiplying, if we take this side, we divided by IN minus. So this particular equation, we are calling it as equation 3. Okay. We are just multiplying the whole equation on log on both sides. What do we get? Log H3O plus is equal to log KIN. And this is in the form of log M by N. What is log M by N? Log M by N is nothing but log M minus log N, right? So same thing, plus log of HIN minus log IN minus. Is there any doubt till here? We are just applying log. So this is in the form of log M by N. Log M by N is nothing but log M minus log N. So what is log Mn? Log Mn is nothing but log M plus log N. So this is log M by N, which is nothing but log M minus log N. So that we are calling it as equation 4. So what do we do later is that we are going to change the sign of this. We are reversing the sign. So what do we get? Here it is plus, so it becomes minus log of H3O plus is equal to minus log of KIN and minus log HIN plus log IN minus. Is it clear? We are just reversing the sign. or multiplying the whole equation with minus. Anything is okay. So what is negative logarithm of H3O plus? It's nothing but pH. Negative logarithm of Kin is nothing but pKin. And this is in the form of log m by n. This is m, this is n because it contains minus. So it is log in minus divided by Hin. Okay. So this in minus or ionization we say only when it gets into the basic pH, and it will be in unionized state whenever it is in acidic medium. So you can just, instead of calling it as in minus, since it takes place at the basic pH, we are just replacing this term with base. And since it is in unionized state in the acidic pH, we are just calling it as acid. So pH is equal to pKin plus log of base by acid, concentration of base by acid. So you expect an indicator to show a middle tint. Middle tint in the sense it's not pink nor it is colorless. So you will get this particular tint when the concentration of acid to base is 1, or when pH is equal to pKin in this case. When these terms are same, log 1, or when pH is equal to pKin. Is it clear? A middle tint, you get a middle tint, that is it's neither pink, pale pink, nor it is colorless. It's just an example of phenolphthalein I'm giving. In any cases, based on the pHs of the particular indicator. So whenever the concentration of acid and base becomes equal, pH will be equal to pKin, or you'll get a middle tint of an indicator. Is it clear? Any doubt? Is it clear?
Yes, ma'am.
Anybody has any doubt?
No, ma'am.
Can I move ahead? Okay. Not only this, the indicators in general, whatever we are calling, for example, phenolphthalein, if you consider, they exist in tautomeric form. What do you mean by tautomeric form? Tautomers. What do you mean by tautomers? Tautomers are nothing but they exist in resonance with each other. That is, whatever atoms are there, they keep resonating. Resonating is nothing but they keep moving. Okay, so phenolphthalein is one such indicator, wherein in unionized form, this is an unionized form of phenolphthalein. It will be colorless. As I said, in acidic pH, it will be colorless. And on adding, on resonating, it will form such ions, red or pink. So it will be this and this. So it keeps on resonating. So as you can see, O minus here, which moves here and forms O minus here. So it keeps resonating. The ionized forms show the change in color. Okay. So the color of any indicator added to the test solution depends on the ratio of ionized to unionized form of indicator present. As I told, most of the cases, unionized form, it will be acidic. On ionization, it is the basic pH. So this in turn depends on the pH of the solution. That is, whether it is in ionized state or unionized state depends on the pH of the solution. So we get maximum sensitivity to pH change when concentration of unionized and ionized are equal. As I said, concentration of the both, when it becomes, what happens? pH is equal to pKa of the indicator. This is what the same thing. When pH is equal to pK of the indicator, both becomes. So now, in general, whenever we say an indicator, there will be change in the pH by, the pH of that particular indicator varies plus or minus 0.5 pH units. For example, phenolphthalein, the pKa value of phenolphthalein is 9.4. And whatever pH range we want, it generally ranges plus or minus this side. That is plus 1.5 minus 1.5. So it ranges 8.2 to 10 approximately. So whatever is the pH we required, the pKa of the indicator, whatever we are taking, so we get plus or minus 1.5 unit difference. So this is how we choose the indicator based on what pH we are taking. The pKa of what, based on the pKa of any particular indicator. If you want pH range this, so you take phenolphthalein. If any like methyl red or methyl orange, based on what is its pKa, we get the pH. Okay, so mixture of indicators can be made which can cover most of the range of the pH scale. So these universal indicators are available as liquids or as test papers, as we said. For example, in general, how does the procedure go on? As I told you, if I give you an unknown solution, how you're going to determine what is the pH. So first and foremost, what you're going to do is that as soon as you get it, you are approximately testing the pH of the solution by the use of pH paper. So you say now I give you an unknown solution. Okay, I give you an unknown solution. What you're going to do is that you're going to take pH paper, you dip into it. So if it's turning blue, what does it indicate? If you are whatever solution I have given you, you are just testing using a pH paper. You dip the pH paper inside the solution, unknown solution. If it's turning blue, what is your conclusion?
Basic, ma'am.
It's basic.
Basic.
So if at all, if it's turning red, what does it indicate? It's acidic, right?
Acidic.
So now you have come to know the unknown solution, it's acidic or basic. Okay, so from the conclusion or like from the confusion of whether it's an acid or a base, you have come to know that it's an acid or a base. Say assume it's a base. Okay, so then what you do is that you prepare series of buffer solution. Okay, buffer solution is nothing but a mixture of acid and base. So in detail we'll study further. So just assume that we are preparing buffer solution, a series of which are differing by 0.2 units. Say now I'm preparing buffer from a pH 0 to pH 14, or if at all if I know that it's an acidic or basic, so I assumed it as basic solution, right? So I'm preparing a buffer solution which ranges from 7 to 14. So what I'm doing is that I'm preparing a series of buffer solution which ranges from 7, 7.2, 7.4, 7.6, 7.8 like this till 14. Is it clear? A series of buffer solution, since we have come to conclusion it's a base, because on just keeping the pH paper, we came to know that it turned blue. Blue indicates it's a basic solution. So what we are doing, we are just preparing a series of buffer solution differing by 0.2 units, okay, to the whole basic range, which is 7 to 14. Is it clear till here? Anybody has any doubt?
No, ma'am.
Okay, then what do we do is that the whatever chosen indicator is there, a basic indicator, we are going to add to all the buffer solution. Okay, we are going to add indicator to all the buffer solution and also to the unknown solution whose pH has to be found. Clear? Then what do we do is that colors of the buffers of known pH, we are going to match with the unknown. So since series of buffer solution we have prepared, so we just compare it with our unknown solution. So say now it is almost, just imagine all is in yellow range. Okay, yellow which is ranging to orange, orange to red. Okay, just imagine from 7 it ranges yellow, pale yellow like that, then it goes to orange. Orange is followed by brown, brown followed by red, something like this. So we just compare, say the unknown color whatever we have got is in the range of orange. In orange we have different range because it's referring by 0.2. On comparison, whichever it is matching with the buffer solution, we are coming to conclusion that that is the pH of the unknown solution by comparing it with the buffer whose pH we know, because we are preparing the buffer differing in 0.2 pH, right? So finally we are coming to conclusion based on comparison of the unknown with that of the known buffer whichever we have prepared. After adding indicator to all, the change in the color of the unknown, we are just comparing it with the buffer to whichever it matches. Finally we are concluding that it is the pH. Probably it might be around 9.8 or 9.6, anything. So whichever, how much ever is the buffer, whichever the color of the buffer solution we have prepared is matching with that of the unknown, we are coming to conclusion that that is the pH of the unknown solution. So this is nothing but a comparison method or comparative method. Okay. So since we are comparing the color of the standard, that is the buffered standard, whatever we have prepared, with that of the unknown solution. So this is a comparative method. So hence by direct comparison, unknown pH can be determined within 0.1 pH unit. So 0.2 differing they are, right? So we will come to know the difference in 0.2 pH. So in general sets of these buffer solution already mixed with the indicator, we do get it directly in the market. What we call it as a capillary tubes, in the sealed capillary tubes in the form of capillators. We call it as capillators, which are available already in the market. So if at all, if you do not have time to prepare the buffer solution in these particular ranges, you can directly get it from the market and directly compare it. Okay, already indicator would be added to the buffer solutions. So you just add the same indicator to the unknown whose pH has to be determined, and you compare with the buffer solutions, whatever you've got it. Okay, so commercially available capillary tubes are known as capillators. So for large volume test liquids, we use something known as comparators. Okay, so comparators are particularly useful when we have a turbid or colored solution. Okay, so this is about colorimetric method. Next is electrometric method. You would have seen this electrometric method somewhere. Have you seen this electrometric method? That is use of electrode. Based on this, you come to know the pH. Have you seen somewhere? No? In any labs? Anyone? You have not seen pH meter? In general, we call this as pH meter. Electrometric method, we use an electrode. So commonly we call that as pH meter. Okay, we'll move ahead. So this electrometric method is the most precise method because it's just a comparative method, right? It's not full to final the exact pH what we get. But in case of electrometric method, we get the most precise answer of pH of the unknown solution. So here what happens is that I'll explain using the diagram. So it consists of two different electrodes. One is known as glass electrode. The other one is known as indicator electrode. Okay, glass electrode or indicator electrode, and another one what we call it as reference electrode. So we have two different electrodes, but in laboratories if you are finding, both will be a single electrode. So it's a sophisticated ones where both the indicator are in the same electrode. Okay, whatever we have in most of our laboratories, both are combined as such. But here, this particular experiment, you have two different electrodes. One is known as the indicator electrode, the other one is known as reference electrode. So indicator electrode is also known as glass electrode, which you can see that it is made up of special type of gas. Okay, it is made up of special type of glass made up of this lithium or rubidium oxides. Okay, so they are made up of lithium, special type of glass made of lithium, rubidium oxide, like that, cesium, such metals. So, and the speciality of this particular glass is that the tip of the glass is blown at the bottom. As you can see, it's not tapering end, it is blown at the bottom, and this blown bottom is usually contains 0.1 normal HCl in it. Okay, this particular this particular glass electrode is being filled at this blown bottom, whatever we are calling, this particular region is filled with 0.1 normal HCl. And what is the speciality of this particular glass made of the cesium or lithium oxide is that it's a permeable glass. Okay, this particular glass is a permeable glass. What does it do is that since I told it is filled with 0.1 normal HCl, it will allow or it will permeate or it will help in permeation of only H plus ion through it. Okay, this particular glass, you can just make H plus ion, movement of H plus ion through this particular glass. Okay, that's the speciality of this particular glass made of lithium or cesium oxide. Okay, this is glass electrode or indicator electrode. Clear? So another one electrode which is connected to this particular electrode, we call it as a reference electrode, which is generally made up of silver chloride, okay, and mercury, which is filled with potassium chloride. Okay, so this is a reference electrode. So that means this is both of these are connected, and these two are connected to a pH meter, where there is a finally this is being connected to a digital display. Okay, so what happens is that these two are electrically connected. So as we know, this particular glass is a special glass which will allow the movement of H plus ion through it. So wherein what do we do is that, understood the construction? If you want, I'll read out. It is the same thing. Yeah. So glass electrode is one of the indicator electrode used for determining pH. The glass electrode consists of a thin glass bulb of special glass blown at the end of the glass tube. As I told, it is made up of lithium, cesium, such, and the bulb is filled with dilute acid. Decinormal hydrochloric acid is nothing but 0.1 normal hydrochloric acid. Okay. A silver chloride electrode, which is the reference electrode, as I told. A silver wire electrolytically coated with silver chloride makes the necessary electric connection with the acid whose pH remains constant. So it has an acid whose pH remains constant, and hence we are going to take this as a reference electrode or a standard electrode. So that means there will be no changes in the pH because of this particular electrode, but we want this to maintain the electric connections with the this indicator electrode. Okay, so several types of glass are used to make pH sensitive glass bulb, and those made of lithia glass are suitable over most pH range. Okay, to measure the pH of the solution, the bulb of the glass electrode and a suitable reference electrode is immersed in the sample. So what do we do is that we take the unknown solution here, we dip the electrodes inside the unknown solution. Just assume that unknown solution is still here. Okay, so this is the unknown solution. Now what happens is that, as we know, this particular reference electrode, there is no change in the pH, or there is no change in anything. So in this particular case, the glass electrode, because the tip of this particular electrode is permeable for H plus ion, whatever unknown solution we have taken from there, as well as from this, that is decinormal 0.1 normal HCl, there will be movement of H plus ions in and around. That is, there will be change or exchange of ion, only H plus ion. Okay, exchange of only H plus ion between the unknown solution and that of the HCl, whichever is present in the bulb here, because of which what happens is that there is a change in the electrical connection, whatever was there, change in the potential between the two electrode, which is being noted. So whatever potential is there, that is being converted to the potential difference, and finally we are going to connect the convert the potential into the electrical connection. It changes electrically, and you get the electrical display, digital display of what is the change in pH in the form of reading. Okay, same thing is being told here. To measure the pH of a solution, the bulb of the glass electrode and a suitable reference electrode, so here we are using silver chloride reference electrode, are connected to a pH meter. So the reference electrode is essential for the second electrical contact with the solution and must have a constant potential irrespective of the pH of the solution. What happens? The two electrodes are dipped in the solution to be tested. If this solution has a different pH from the solution in the probe, on electrical potential results. Thus, the potential between the two electrodes varies with the pH of the solution under test. So